All right, welcome back. Part two of influence lines for statically determinate beams using Muller-Breslau. And, in the first video, we went over and just talked about it, what it was, and did a very simple example and showed you a very simple proof. And now we want to go over some of the finer details about applying Muller-Breslau and just what it means and how to do it, right? That's usually the hard part. Everyone can explain what it is, but how do you put it into action, right? How do you make it work? So here, let's take, for instance, this simply supported beam again. And let's say I have a point C here. And what I'd like to do is find the influence line, IL, for the internal shear at C. Now, one of the things you have to remember is what is positive sign convention for you. And this could be different depending on the textbook you use, the country you're watching this video in. Okay, but here I'm going to be using this sign convention here, where if I make a cut on the inside, right here, and all my videos use this sign convention as well, right here, is that internal positive shear on the left side of the cut is downwards, internal positive shear on the right side of the cut is upwards, normal force, I'm not going to draw that one right now, but here, positive moment is compression at the top, right here. And normal forces would be causing tension on each surface. So this is positive sign convention. And that's important, okay? The other thing you have to remember is, going back to this part right here, is this unit displacement. Okay, that total displacement of whatever it is that you do has to be 1. So when we did this example here and we moved this reaction AY, wherever that reaction or that action was removed, we had to apply a unit displacement, or a unit displacement had to occur. And so if you do a moment, it has to be a unit rotation, okay? So if I want the internal shear here for VC, I essentially have to release. I have to I want the internal shear at VC. I have to redraw the structure to reflect this release of shear capacity at point C. And what would that look like? That would look like this here. Let's see here. Let me draw this. I'm gonna, bam, right about here. I'm gonna draw this. Draw some wheels, a roller, bam. Okay, those blocks indicate that I can transfer some moment still. And I've got this right here. Okay, right here. And boom. And the roller right here. Right here. And this is that point C still right here. Here is still A. Here is B. And the distances are still there. Okay. And so I want to find the influence line for this internal shear at C. I've redrawn my structure. I've identified where the action is that I want to remove. I've removed it, redrawn the structure here. So if I have internal shear that I want to move, I have to maintain the ability to transfer axial forces and moments across this connection. That's what these blocks do. Okay. And these rollers. So essentially this thing can only slide up and down, but it cannot rotate right here. And what I want to do is say essentially that I have, and I'm going to tell you right here, the shear goes this way. So Muller-Breslau, and then the shear at C goes this way here. So internally, it kind of look like this VC. This is how it would look on each side of that cut. So if this is my cut, this VC. And Muller-Breslau simply says that, hey, once you have this right here, you move this side down in the direction of that shear and this side up in that direction of the shear, so that my influence line would look like, let's see here, let's draw this down here a little bit, because I want to differentiate that between the um, the deflected shape. There's a little bit that we need to understand about the deflected shape here. So here is my, boom, here's that spot right here. So wherever I have this point C right here, okay, on the right side of point C, if you will, I'm going to go straight up. Okay, I'll go straight up right here. And on the left side of point C, I go straight down. Bam, right here like that. Okay. And so essentially, and I have to respect the boundary conditions at A and B. So that means point A cannot move, point B cannot move. And so my deflected shape here would be that this member right here would rotate down and look like this. And this would rotate up. Member BC would rotate up and look like that. Okay? And this total displacement is 1. That's unity, or 1. That's that unit displacement that Muller-Breslau talks about. This is the general shape of the influence line. Okay, but we also, and so, but truly the deflected shape it really looks like this. The deflected shape, actually, here, I'll draw it in green this time, or how about purple? Let's use purple here. Let's see, it's going to be boom, like this, okay? And then I have to maintain here, the slope of this line has to be the same as the slope of this line here. And really what it looks like is the deflected shape for this, as you can imagine, actually looks something like this, okay, where these are still 90 here and 90, because, as this member BC rotates up or moves up, it can't stay the same length. It can't just start automatically elongating right here. So this is really this 90 degrees. And this slope right here, this slope has to be the same as this slope right here. And what that means even more right here is that this right here, and if this total distance right here, this total distance is 1 right here, that means if I extended this line out, so hopefully this won't get too messy here, but if I extend this line out like this, okay, so if I extended this line out all the way right here, relative to the original beam, this distance right here is 1, and the slope of this deal right here is 1 over L. Okay, does that make sense? Because these slopes are the same, okay, right here, this slope right here and this slope right here, this is just 1. And the same thing goes if I were to extend this line out, down, like this, this distance right here is also 1. Now, what the heck does that mean? That means that if I go down here, right here, to, let me use, oh gosh, let me use green for the slopes here. This slope right here is 1 over L, okay? Or this angle here, this rotation or whatever you want to call it, is 1 over L right here. This is, I'll call this theta B. Theta B is 1 over L, and that means this height right here, from here, that height right here is just, the distance, this arm, this length right here, this length, we said, this length is B, and that means this distance is just B over L. So now we have a value for here, and this distance over here, because, technically speaking, this is a negative 1 over L right here. This would be a negative 1 over L, because decreasing slope, going left to right. But here, this angle right here is also, theta A is 1 over L right here. That is equal to 1 over L. And this distance over here is negative A over L, right? So this distance right here, if I call, you just multiply the length, which was right here, this A, this arm, assuming small rotations and everything, you just take this length A times this angle right here, and you get negative A over L. And now you have values, right? You have values, so that if you had a specific, separate, it's like point C, we're not in the middle or somewhere, you can calculate specifically a quantified influence line. Bam! That's amazing, right? That's fantastic. Well, shoot, let's keep going. All right, let's see what it's like if I want to find the moment now at C. So if I want to instead now find the internal moment, find now the for the influence line for the internal moment at C. So the moment at C here. Okay, and so here, I have the beam structure here, A, B, C, length A and length B and all that other business right here, right? But now I got to redraw the structure again right here. Bam, let's do that right here. Here's A, or here's A, and here is B. And at point C, I want to release the moment, okay? I want to, again, I've identified the action. I want to redraw the structure without that capacity, with that release. And a moment release, it means essentially I want that moment at that point to be 0, which is essentially a hinge, right? And so this hinge Boom. Right here. Let's see. Let's see if I can make it. Let's give that the color blue. And then let's say that it's got some boundaries on the sides here. Okay. Some little blocks here, some boundaries. And let me draw that a little bit better. Bam. And the hinge here I have here. And essentially what I want to do now is reapply that moment. These are my moments at C, my moment at C with the cut. Okay, so you can see on the right side of the cut, I have this compression at the top. I've redrawn the moments at the in their positive sense. Okay, using the sign convention. And here, just to again A, B, and here's point C. Okay, and really what I want to do, what's essentially going to happen is, I want this vector, if you will, is this moment is a vector that's out of, it's pointing out of plane. It could be placed anywhere in the beam. So all it does is it causes this segment AC to rotate. So this segment AC, if it had no boundary conditions, would just rotate like this. Okay, it might just rotate like this. All right. But I can't. I have boundary conditions. I have a boundary condition at A that says this beam can't move up and down. So really, what happens here is I erase that dotted line, and I have to shift that dotted line up so that point A has zero displacement. So here, bam. So my influence line looks like here at C, like this, right there. Okay, right there, and here, same thing with B, right? It's like I wanna rotate segment BC in the same direction as MC right here, this portion right here, but I have to respect the boundary condition at B. So it looks like this. Oops. Bam. Okay. And there is my influence line, my qualitative influence line for the moment at C due to a moving unit load, right? Now we want to also, take one step further and get some values off of that, right? We want to get some values, otherwise, what's the point? So using Muller-Breslau, if we know that these segments here and here have the distances, we'll say A and B, and this has some height that I have no idea what it is, right? This point C, this new point C, if you will, has some height H, okay, which really still remains unknown to us. But I can go ahead and say, oh, the angle theta A and here theta B. So I could say theta A, if I have small deformations, is just H divided by A. Yeah, I think that's opposite over adjacent. Yeah, that sounds good to me, right? And theta B is H divided by B. Okay, that's great. That's amazing, right? And what's more is that we had this one little rule that the moment had to have or this whatever we remove had to be replaced by a unit displacement, but in this case a unit rotation. And here, that rotation has to be relative to the other beam. So here, if I have this segment AC, I need segment BC to have rotated a unit rotation. This total angle is equal to a unit rotation. Theta equals 1. And so, you're probably going, "Oh, I get it now," right? But what that means is that this theta right here, this theta is equal to theta is equal to 1, which is really, if you just use similar triangles or just whatever, any law, parallel lines and all this angle stuff right here, right? Theta A plus theta B, okay? And that's it. And then you would just have that here, and you can solve for H, essentially. That's what I'm trying to tell you. Here is that theta A plus theta B equals 1, which means now you could say H over A plus H over B equals 1, and you can solve for H from here. Solve for H. That's it. And then you would have values. You would have values for the entire influence line. Okay, so hopefully that was useful in a qualitative sense and with a way to quantify the influence lines. then in the next videos, we'll do some examples that are complicated and really, well, they're not complicated. Once you can apply Muller-Breslau, that's it. So hopefully you've enjoyed. All right, see you in the next video.